The main job of the lungs is gas exchange, pulling oxygen into the body and getting rid of carbon dioxide. Normally, during an inhale, the diaphragm contracts to pull downward and chest muscles contract to pull open the chest, which helps suck in air like a vacuum. And then during an exhale, the muscles relax, allowing the lungs to spring back to their normal size, pushing that air out. When you breathe in, air flows through the nostrils and enters the nasal cavity, which is lined by cells that release mucus. That mucus is salty, sticky, and contains lysozymes, which are enzymes that help kill bacteria. Nose hairs at the entrance of the nasal cavity get coated with that mucus and are able to trap large particles of dust and pollen, as well as bacteria, forming tiny clumps of boogers. The nasal cavity is connected to 4 paranasal sinuses, which are air-filled spaces inside the bones that surround the nose. There's the frontal, ethmoid, sphenoid, and maxillary sinus. The paranasal sinuses help the inspired air to circulate for a bit, so it has time to get warm and moist. The paranasal sinuses also act like tiny echo chambers that help amplify the sound of your voice, which is why you sound so different when they're clogged with mucus during a cold. So the relatively clean, warm, and moist air goes from the nasal cavity into the pharynx or throat. The region connecting the two is called the nasopharynx, and the part connecting the pharynx to the oral cavity is called, you guessed it, the oropharynx. The soft palate, the softer portion of the roof of your mouth behind the hard part that you can feel with your tongue, and the pendulum-like uvula hanging at its end move together to form a flap or valve that closes the nasopharynx off when you eat to prevent food from going up into the nasopharynx. Finally, there's the laryngopharynx, the part of the pharynx that's continuous with the larynx or the voice box. Up to this point, food and air share a common path. But at the top of the larynx sits a spoon-shaped flap of cartilage called the epiglottis, which acts like a lid that seals the airway off when you're eating so that the food can only go one way, down the esophagus and towards the stomach. If anything other than air enters the larynx, then there's a cough reflex to kick it right out. Now, once air makes its way into the larynx, it then continues down as the trachea, or the windpipe, which splits into the 2 main stem bronchi. The point at which they split is called the carina. They then enter the lungs, and the right lung has 3 lobes: upper lobe, middle lobe, and lower lobe, and the left lung has just an upper lobe and lower lobe. The right mainstem bronchus is wider and more vertical than the left, which is why if you accidentally inhale something big that can't get coughed out, like a peanut, then it's more likely to go into the right lung than the left. The mainstem bronchi then divide into smaller and smaller bronchi. The trachea and the first 3 generations of bronchi are all pretty wide and use cartilage rings for support. Taking a look at a cross-section chunk, there's also a layer of smooth muscle which has nerves of the autonomic nervous system within it. The autonomic nervous system is made up of 2 basic types of nerves: sympathetic nerves, which are involved in fight-or-flight mode, like running from a turkey, and parasympathetic nerves, which are involved in the rest and digest mode, like eating ice cream at the beach. Smooth muscle along the trachea and the first few branches of bronchi have beta-2 adrenergic receptors and muscarinic receptors. Going back to that turkey, when you're running, the sympathetic nerves stimulate those beta-2 adrenergic receptors and increase the diameter of the airways. When you're relaxing on the beach, the parasympathetic nerves stimulate the muscarinic receptors, causing a decrease in the diameter of airways. The large airways are lined mostly by ciliated columnar cells and a handful of goblet cells, which get their name from looking like a wine goblet or glass, and secrete mucus. That mucus helps trap particles, and then the ciliated columnar cells beat rhythmically together to move the mucus and any trapped particles from the air towards the pharynx, where they can either be spit out or swallowed. This mechanism is known as the mucociliary escalator. After the first 3 generations of bronchi, however, the airways become more narrow, called bronchioles, little bronchi, and these can stay open without the need for cartilage. Air is conducted through smaller and smaller bronchioles for about 15 to 20 generations, and collectively they're known as conducting bronchioles. The bronchial arteries supply the conducting bronchioles with oxygenated blood. Now, the walls of the conducting bronchioles are similarly lined by ciliated columnar cells and mucus-secreting goblet cells, as well as a new cell type called club cells because they look like tiny clubs. These club cells secrete glycosaminoglycans, which is a material that protects the bronchiolar epithelium. These guys can transform into ciliated columnar cells, so they help regenerate and replace damaged ciliated columnar epithelial cells if needed. The last part of the conducting bronchioles are the terminal bronchioles, and then after that, air gets to the respiratory bronchioles, which are unique because they have tiny outpouchings that bud off of their walls. These outpouchings are called alveoli, and there are about 500 million of them within the lungs. Eventually, the respiratory bronchioles ends when there are nothing but alveoli, and at that point, the airway is called an alveolar duct rather than a respiratory bronchiole. This is the final destination of the inhaled air. The alveolar wall has a completely different structure from the bronchioles. There are no cilia or smooth muscle, and instead the wall is lined by thin epithelial cells called pneumocytes. Most are regular pneumocytes called type 1 pneumocytes, but some, called type 2 pneumocytes, have the ability to secrete a substance called surfactant, which helps decrease the surface tension within the alveoli and keeps them open. Like the club cells, the type 2 pneumocytes are capable of transforming into type 1 pneumocytes, so they can also help regenerate and replace damaged cells. Finally, if a tiny particle ever makes it deep into the lungs, there are alveolar macrophages that can gobble it up and then physically move up to the conducting bronchioles, where they can ride the mucociliary escalator all the way up to the pharynx to be either coughed up or swallowed down. Free from particles, the inhaled air is now in the alveolus, surrounded by mostly type 1 pneumocytes. On the other side of the pneumocytes are endothelial cells that line the capillary walls, which is where that sweet, sweet blood is. This time, though, that blood comes from the pulmonary arteries, carrying deoxygenated blood. The pneumocytes and the capillaries are glued together with a protein layer called basement membrane. So the alveolar wall, the basement membrane, and the capillary wall is really all that separates the air from the blood, and this is called the blood-gas barrier. At this point, carbon dioxide diffuses out from the deoxygenated blood and into the air of the alveoli, which then gets breathed out. And with each breath in, oxygen enters the alveoli and freely diffuses into the blood. That freshly oxygenated blood then heads off to the pulmonary veins, the heart, and then to the body's tissues. Alright, as a quick recap, the respiratory system facilitates gas exchange. Oxygen in the air is inhaled and makes its way through the pharynx, larynx, trachea, large upper airways, conducting bronchioles, respiratory bronchioles, the alveoli, and finally the capillaries to be sent to the body's tissue. Then carbon dioxide makes the reverse journey to eventually be exhaled into the world.